Hello everyone. Myself Ashish Chaudhary. I will be the PMRF TA, so one of the PMRF TAs for this course for this semester. The name of the course, as you all know, is Geology and Soil Mechanics, and the course instructor is Professor Priyank Ghosh of IIT Kanpur, and myself, I am Ashish Chaudhary. Uh, I am doing my PhD here at IIT Kanpur. Okay, so uh, we will be having 12 discussions or 12 problem solving sessions corresponding to 12 weeks of lecture. And apart from that, we will be having one more, one extra actually summary session of 1 hour duration at the end. So all of the discussion sessions will be 2 hour long, and the summary session on the 13th week that will be 1 hour long. So uh, let us start. So in the first week, you might have seen all the lectures. So the first week lectures are actually nothing but basic introduction. Is nothing but the basic introduction of geology and soil mechanics. So initially the first week was only most of the part was just about the geology part, right? So we began with the uh, type of rocks, then how soil is actually formed from rock. Okay, what are the different processes? We learned about the formation, soil formation. Then we learned about certain properties which are known for, which are very much necessary for classifying a type of soil. Those are the index properties. And after the index properties, some problems were actually solved in the class, right? So today, what we will be doing is that the initial 1 hour, the first 1 hour, till around 7 o'clock, we will be discussing revising ones. Okay, we will be just recapitulating whatever has been taught in the first week lecture. Okay, and uh, uh, and after that, we will be solving some problems. Okay, some demo problems in the second half. Okay. So this week everything is basically very much easy, right? Very simple. So if we have gone through the lecture, you already know that these things are actually very easy and very basic, right? So we will be seeing all these things, and uh, then after so as the course progresses, our the difficulty level will actually increase a little bit. So then we will be actually uh, learning various concepts on soil mechanics. Okay, so slowly the difficulty will increase, but what we will do is that we will be solving as much problems as we can, so that all of your doubts are actually cleared. Okay, so let us start today's session by revising whatever has been taught in the lectures actually. Just a second. So basically, so in the first week, as you all know, we discussed about the engineering geology of the soils and their formation and the clay mineralogy a little bit. Right. So let us begin. So how is actually soil formed? Okay. If you want to know how is soil actually formed, the soil is basically formed from disintegration of rocks. Right. So uh, so the rocks actually they undergo a process known as weathering. Okay, so because of weathering, these soils are actually formed from rocks. And so rocks are the initial, the primal stage. From rocks, actually, soils come, right? So rocks can again be classified into three types, right? So first is igneous rock, sedimentary rock, and then we have metamorphic rocks, correct? So what are igneous rocks? What are igneous rocks? Igneous rocks are formed due to the solidification of molten magma, right? That comes out from the deep layers of the earth, right? So as you know, earth we have a core which is a solid ball, then we have a mantle layer which has some liquid magma flowing, then we have the crust, right? So the when the this molten magma it comes out of the earth, means comes out at the surface, it solidifies and eventually forms igneous rocks, right? And then we have the sedimentary rocks. So what are sedimentary rocks? Sedimentary rocks are formed when this gravels, sand, all these things, they get deposited layer by layer. Okay, these get deposited layer by layer, and due to the overburden pressure and due to the cementing effect of various minerals and other agents, these rocks are formed. So these are called sedimentary rocks, right? And the last we have this metamorphic rocks. So the metamorphic rocks are actually formed from sedimentary rocks or from igneous rocks due to a process known as metamorphosis. So metamorphosis means there is some chemical change in the mineral structure of the rock that happens due to high heat and pressure. Okay, due to heat and pressure, these changes take place, and then we have a totally different type of rock, where the chemical composition of the rock is totally different from the parent rock. So those are called actually metamorphic rocks. Okay, so how are soils formed? Soil is actually formed due to resinous weathering. Right. So weathering can actually be chemical or it can be mechanical. Okay, so chemical weathering or mechanical weathering. So in chemical weathering, what happens? The original, as I said, the original constituents of the rock are actually transformed into newer constituents due to some chemical reaction. So that is chemical weathering. And in mechanical weathering, what happens? The parent rock actually gets disintegrated due to uh, uh, some agencies such as say air, then wind, this wind, then water, river. Okay, river flowing through a water, river flowing would actually act as abrasing agent over the rock, and then the rock would actually disintegrate. Right. Okay. So uh, soil formation. So as I said, chemical weathering or mechanical weathering. Okay, this can be the main two processes due to which soil is formed. And one more can be soil can be of organic. Okay, the soil can actually originate from organic material, right? So organic materials such as say plants that are decomposed years and years, they get deposited and finally they form organic soils. Okay. Now, a soil which is actually found at its native place is actually known as residual soil. Then, if the soil is actually transported from one place to another, from where it's formed and then where it's found, that is called transported soil. Right. The transportation can be further classified as alluvial deposits, lacustrine deposits, marine deposits, right? Aeolian deposit and glacial deposits. So I won't repeat all those things. They're very simple. You might have already gone through the lecture. Okay. Now let us come to the main basic, okay, the main basics of soil mechanics. Okay, so first we start with the soil as a three-phase system. All right, so we start with this. So generally a soil, okay, so here you can see here we have shown a soil mass. Okay, the soil mass actually consists of three constituents. One is the soil solids, the water, and the air. Okay, so these grains, these actually form the soil solids. Okay, these grains actually form the soil solids. Then we have this portion. Okay, we have these spaces. This space is nothing but the void. Okay, these spaces are nothing but the voids, right? Empty spaces. Now, these voids can either be totally empty, that is, it can be void, or it can have some water, okay, in it. Okay, so it might be empty, that means there is air. So these voids can have air or water or only or both. Okay, only air or water or can have both. Right. So here, whatever you see, this is nothing but the phase diagram. So this is called a phase diagram. All right, so this is called a phase diagram. Say this total this is a volume V. Okay, total volume V. Out of this much volume is actually occupied by the solids. and this much volume is actually occupied by the voids. This volume of voids can be further divided into two regions, right? Volume of air and volume of water. Similarly, this is the total weight W. Here we have the weight of solids and we have the weight of water. We have the weight of air. So air is weightless, we can consider, so it can be zero. Right? So weight of void is equal to weight of water plus weight of air. This is zero. So this is what? Okay. Now we call a soil fully saturated if. So what is the volume of voids? Volume of just a second. So volume of voids is nothing but volume of water plus volume of air. Right. So now if everything, so if air is not there, okay, see if this is zero, this total portion, the total volume of voids is volume of water. Then we call it as fully saturated. Okay. And if volume of voids is completely volume of air, then we say this is a dry soil, means no water. Right. So these are the three possible scenarios. So partially saturated. So in the volume of void, some portion is occupied by water, some portion is occupied by air, or we can have fully saturated, where the total volume of void is occupied by air, or we can have totally dry soil, where total volume of voids is actually occupied by air. All right. Now, there are some important properties. Okay, the important properties, very important properties of soil that we actually must know. Okay, there are some very basic. Okay, so these properties are called index properties. Now, to obtain index properties, we need to do some tests. So the test carried out in order to classify a soil are termed as classification tests. Okay, and the numerical results that we obtained on the basis of such tests are termed as index properties of soil. All right. So what are the index properties? Let us see one by one. So first is the water content. So water content, what is water content? Water content is nothing but weight of water by weight of solid into 100%. Right. So what is the lower limit? Lower limit is what? 0. For a completely dry soil, the water content is 0. The lower limit is what? 0%. And what is the upper limit? What is the upper limit? Is there any upper limit fixed? Is it 100%? Is the upper limit 100%? What do you think? Is the upper limit 100%? No, right? The upper limit is actually infinite, to anything. Infinity. It can be anything, right? Bit of water can be anything. Anything you can put. How much water you want to put, you can put. No, so there is no upper limit. Then we have the void ratio. What is the void ratio? It is very important. Volume of voids by volume of solids. Right? So what is the lower limit? What is the lower limit? There will be some lower limit, right? 0 is not the lower limit. Some finite value. And what is the upper limit? Same, no upper limit. There can be any volume of void, right? There is no. Next, we have the porosity. So porosity is similar to void ratio. So porosity is nothing but volume of voids by total volume, right? So obviously here you can see, say this is the solid, this is the voids, right? The total. So volume of voids by total volume. So what is the upper limit? So upper limit is definitely less than 100%, right? So you can have, say, like up to here, the volume of voids can be very high, solids can be very low, but it won't be so. Void means what? Just void, right? Nothing. If there is nothing, there is nothing only. So volume porosity is always less than 100%. And lower limit also not there, right? Some definite value will always be there. The next is degree of saturation. So degree of saturation is what? Water. Now again, if I want to draw, it is completely right. A volume of water by volume of void. So lower limit can be 0 and upper limit can be 100%. Okay, so 0 to 100%. Next we have air content. Air content is nothing but volume of air by volume of voids. Okay, volume of air by volume of voids, nothing but 1 minus degree of saturation. Similarly, percentage air voids, nothing but volume of air by total volume into 100%. Okay, now we have come to the unit weights. Okay, we come to the unit weights. The first is the bulk unit weight. Okay, so it can be gamma T or T, or if you call it density, then it can be. Okay, so this is nothing but total weight by volume, weight per unit volume. Weight is composed of this. composed of this, right? So this is the bulk unit weight. Weight per total weight per unit total volume. Next we have the dry unit weight. The dry unit is nothing but weight of solids. Why? Okay, weight of solids by total volume. Then we have saturated unit weight, gamma saturated. Think about the saturated weight, right? And submerged unit weight. Think what? W submerged by. So submerged is nothing but gamma sat minus 9.81 kilonewton per. Yeah, so this is total volume. Okay, submerged weight by total volume. Similarly, unit weight of soil solids, weight of solids by volume of solids. And specific gravity of solids, GS. What? Weight of solid. So volume of solids to gamma W. It can be written as gamma solid by, because this is nothing but this. Right, so generally GS is between 2.65 to 2.80, general range. Okay. Just give me 1 second. Okay, so next one more very important topic is the grain size distribution curve. Okay, the grain size distribution curve. So what is the grain size distribution curve and how do we get it? So grain size distribution curve of a soil is nothing but the classing but the distribution of the constituent size of all the particles or all the grains that form that soil. Okay, so we plot a curve which shows us what size of soil particles are there in that particular soil. Okay, in that particular soil mass. All right, so that is nothing but the grain size distribution curve. Now, in order to obtain the grain size distribution curve, what we need to do, we need to do the sieve analysis. Now, sieve analysis is dry analysis or wet analysis. So, dry sieve analysis actually done for coarse soil or wet. Then we have the hydrometer. analysis which is done for fine grained soil. So what is coarse soil and what is fine grained soil? We will discuss that. Okay. So generally, all soil actually contains both coarse part and the fine part also. Coarse fraction also and fine fraction also. So what we need to do initially, we do a dry sieve analysis. Okay. From the dry sieve analysis, we get a fine fraction, and then at fine fraction, we actually do hydrometer analysis to get the distribution for that fine fraction. Then we combine everything to get the total grain size distribution plot. All right. So we'll discuss everything slowly. So this sieve analysis should actually be done through IS code IS 4601962. Check if this is revised or not once. Okay, just check the latest version once. Okay, so what we do, we just use with various sizes of sieve. What is sieve? Sieves you might have seen that we used to pour tea or something to this sieve the tea. Okay, tea while we pour it in the cup. So that is a sieve, right? We use various sizes of sieve, okay, to do the dry sieve analysis. Okay, so the sizes of sieve actually are from 80 to 75 microns. Okay, literally 75 to 10 to the power minus 3 mm. Okay, 80 to 75 micron. Okay, so 1 micron is nothing but 10 to the power minus 3 or 10 to the power minus 6 meters. Okay, nothing but micrometer. Okay, that's why sometimes you write this mu sign. The first what we do, we take a certain amount of sample, right? That sample is actually sieved. Okay, sieved through 4.75 sieve. Please listen to this very carefully because these things are actually necessary for soil classification. Okay, so we'll be seeing how to classify soil, right? So this is actually very much important for the soil classification portion. Okay, okay, so this will be very much necessary for soil classification. So just pay attention. Okay, here. So first, what we do, first we sieve through 4.75 So the fraction that is retained on the 4.75 sieve, that is soil particles whose size is actually greater than 4.75 that fraction is actually known as gravel fraction. Okay, so for that portion which is retained on the 4.75 sieve, we need to use further sieving. We need to do further sieving in this order. Okay, for with these sieves. For that retained portion, right? And the part and the fraction that passes through 4.75 that is the sand fraction actually. Okay, sand fraction. So for the material that passes through 4.75 we need to do the fine sieve analysis. Okay, the fine sieve analysis. The fine sieve analysis, this is for the coarse sieve analysis. For the fine sieve analysis, the sizes of the sieve are 2 1 600 microns, 425 micron, 212 micron, 150 micron, and 75 micron. Okay, sorry for the bad writing. I will just write it again. Okay, 1 mm, 2 1 is 600 micron. Okay. 75. Right? Okay. Okay. So what we do is that, see, I've written here. Do the what is required to be done to obtain the green size distribution analysis? Do the sieve analysis or the hydrometer analysis or both. For coarse, we do the sieve analysis, and for fine, we do the hydrometer analysis. The sieve sizes, all the sieve sizes are written here. If the soil passing through 75 micron is higher in quantity, that means a large amount of fraction is actually smaller. Okay, large amount of soil fraction is actually smaller than 75 micron. Then we need to go undergo wet sieve analysis and hydrometer analysis. So, so size lower than 75 micron means this is the clay fraction. We call this as clay fraction. So greater than 4.75 mm, that is the gravel fraction. Between 4.75 to 75 micron, that is the sand fraction, and lower than 75 micron, that is the clay fraction. Okay, the clay fraction. Now what we need to do, we need to just make a table. So we know a particular quantity of soil that we have taken. Then what we do, we just write all the sieve sizes here, like this, like this, like this. We will write. Okay. Then we will write here. We will write the weight retained in all the sieves. So we'll write all the weight retained in all the sieves. Then we have the percentage weight retained. How will you get the percentage weight retained? Weight retained divided by the total amount of soil mass that we have taken, right? That will give you the percentage soil retained. Then we have to do the cumulative percentage weight retained. Okay, we'll get the cumulative. So this, then this plus this plus, and the cumulative weight retained, we have to write them. Okay. Then what we need to do, we need to find the percentage finer. That is 100 minus the cumulative weight rate. It will give us the percentage finer. So we got the percentage finer and the sieve sizes, right? So if you know the percentage finer and the sieve sizes, we can have the grain size distribution plot. So here is the percent finer and we have the size here, sieve size. So we will get a plot like this. Okay. Now the Now say most of the like a large quantity of soil is actually passing through 75 micron. So what we need to do, we need to do the hydrometer analysis. Before that, what we do, so there is a sieve, 75 micron sieve. So a large amount of soil has passed through 75 micron sieve, and some amount has got retained also on the 75 micron. So what we do, whatever is retained on this 75 micron, we wash it with water. Because sometimes what happen, very small particles they stick to each other and they form a large particle, and then they don't pass through the sieve. Okay, they coagulate, form a large particle, then they don't pass through the sieve. So what we do, you take some distilled water and then just wet the soil that is written on the 75 micron sieve. You take some distilled water and then you wet the soil that is there. Right. So what will happen? As distilled water is non-ionic, right? So non-ionic, so it will not help in coagulation. Okay, so it will be just a neutral agent. What will do, the all particles, it will just come, like those that are sticking to each other, that will actually get separated, and then some more particle will actually pass through 75 microns. We'll see that. Okay, that's some more. Just a second. Okay, just 1 minute. Just a second. Just a second, huh? Just give me a minute. Yeah. So as I was saying, as I was as I was saying that a lot of now after washing, you will see more amount of particles is actually passed through the 75 micron. Okay. So after that, what we have to do, we need for the portion of the this soil that is past to 75 that we need to oven dry that. Okay, we just oven dry that sample. Oven dry that sample and then take the weight. You dry it in the oven, okay, and then take the weight. After that, what we need to do, you need to do the hydrometer analysis. So what is hydrometer? So hydrometer is a very delicate instrument that is used to measure the it is used to do this hydrometer this analysis. Okay, this wet self analysis, hydrometer analysis. Okay, this is a very delicate instrument that actually works on the basis of Archimedes principle. Okay, Archimedes principle is nothing but what is Archimedes principle? So there will be whenever you submerge something in a liquid, there will be buoyant force. So what is the buoyant force? The buoyant force is nothing but equal to the weight of the volume of the water, that water or the liquid that has been displaced by that by that object. Right? It works on the basis of Archimedes principle. So the hydrometer actually looks like this. Okay, this is made of glass, very delicate instrument. It is made of glass, and this look like it is a bulb. It is a bulb, and then it is a graduated cylinder like this at the top. At the bottom, it has a bulb. So what we do is that we actually relate the reading. Okay, reading. Okay, this reading RH, the reading that we take at the level. So wherever the water is actually intersecting that hydrometer, we take the reading. That reading is RH. So that reading we actually correlate to this effective depth HE. We correlate to this effective that HE, and that effective that HE is actually related to the particle diameter. We'll see that. How- how. Okay. So what we do is that we take a jar, 1 liter jar we take like this. We take a jar and we take distilled water in it. Distilled water, and then we take a certain amount of the dried portion. Okay, some specific some certain amount of certain weight of say 100 grams of the dried soil that has passed through 75 micron sieve. That amount of soil we take, and we make a solution. Also, we put some non-coagulating powder agent, non-coagulating agent in there, so that these particles actually do not flock together and coagulate. Okay, there is no flocculation. So non-flocculating agent, some non-flocculating agent is actually given. Okay, now this RH is actually related to this HE, this effective height. So this is actually obtained from the calibration chart. So this calibration chart is specific for every hydrometer at a particular temperature, for every temperature. Okay, for the standard temperature, this calibration chart for a particular hydrometer that you can get. All right, that you can get. So this H is nothing but H1 plus. Okay, this is a calibration chart or calibration plot. Now what we need to do after we get this RH, after we see this RH, so this is submerged like this, right? We submerge something like this. And so we get the reading here. Okay, we get the reading here. This is RH. So as the particles keep on settling down, what happens is that this HE, this effective depth actually keeps on increasing. Its effective depth keeps on increasing. Now, after we read the RH from here, what we need to do, we need to correct it. So the corrected hydrometer reading is nothing but the RH plus Cm plus minus Ct minus Ct. Cm is nothing but the meniscus correction. So there is a jar, you have a tube like this something, and you have the water, right? So this is a colloidal water, right? So generally what? Generally we have to read the lower meniscus, right? Wherever this lower meniscus of the water is touching the hydrometer. But that is not possible because the water is actually very clouded. So this we have to give some meniscus correction. Okay, then we have the plus minus temperature correction. So generally the hydrometer is calibrated. Okay, the calibrated at 27 degrees Celsius. So if the temperature is higher than 27, then we have plus, or if it is lower than 27, the room temperature where you are conducting the experiment, that is lower than 27, then we have minus. Okay, subtractive. And the last we have the dispersive agent. Okay, dispersive agent or the non-foculating agent that I was talking about, that correction, that is always minus. So now this corrected, this one can be used to obtain the HE, effective depth. Now if you know the effective depth, okay, certain centimeters, what we can do, we can get the size. Okay, so it come from Stokes law, we can get this. Just check this, check this, check it. Okay, one, check this formula once. So this is the viscosity of water. So using that, so what we do is that at equal intervals of time, we keep on taking the reading and we keep on noting the result. So it's say at 5 seconds we take the reading, then at 10 seconds, then at 20 seconds, then at 40 seconds, then at 80 seconds, at 160 seconds. Like this, we keep on taking the reading. Okay, we keep on taking the reading of RH at equal intervals of time. Okay, at certain intervals of time, we keep on taking the reading. Then what we can do, we can correlate this time. We can correlate this time with this HE, which is related to RH, to the diameter of the particle size. Okay, the size of the particles. Okay, so from there, after we have determined D, what we can do, we can get the percentage finer. Percentage finer than D. N is nothing but GS by GS minus 1 into RC by NW into 100%. So what is this W? Weight of solids per cc in original suspension. Okay, so we get the percentage finer than D. So now for this D size, we know the percentage finer like this. Many D's we will get and many percentage finers we can get. So finally we can get the total grain size distribution curve. So I hope this is clear. If it is not, then what we can do is that we can see some videos. Okay, some videos. There are many videos available on YouTube. So it's extremely very difficult to explain like this. You have to actually do it and explain. And I hope that in your geotechnical lab this will be done. So this will be like, this is quite easy, right? This is quite easy. So it will be crystal clear to you. Okay, this will be done in your geotechnical labs, obviously. Now there are some important parameters. Okay, important parameters that can be obtained from the grain size distribution curve. These are very, very important. Okay, you need it throughout the course. You need to remember these things. There are some various very, very important parameters. So there is a size called the D10 size. Right, this D10. So what is D10? So we have percent finer and size. It will be something like this. So what is D10 size? The size corresponding to 10% finer is nothing but the D10 size. Similarly, the size corresponding to 60% finer is D60, 30% finer is D30. So D10 is called the effective size. Okay. And there is a term called coefficient of uniformity, which is nothing but Cu is D60 by D10. For okay, I will tell just. And one there is the coefficient of curvature. Think what Cc D30 square by D60 into D10. So now for a well graded soil. So well graded means what? Well graded means there are good fractions of all sizes of the particles that are present in the soil mass. A good fraction of all sizes are present. That is the well graded. Okay, gradation is good. So for well graded soils, for sand, Cu should be greater than 6 and Cc should be between 1 to 3. And for gravels, Cu should be greater than 4 and Cc should be again between 1 and 3. Okay, then we have poorly graded. Poorly graded means what? Only some particle size are present. Okay, some. And other is the gap graded. Gap graded means some sizes are actually missing in between. That is the gap graded. Okay. 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 This is all about the grain size distribution curve. Okay. Next we come to the consistency of clays. So what are clays? How are clays? Clays means what? Lesser than fraction lesser than 0.75 mm. Sorry, so from 0.75 mm, that is 75 micrometers. Particles, if the constituent of a soil is such that most of the particles that make that soil, that build that soil, is actually lesser than 75 microns, then we call it as clay. Okay, we call it as clay. Okay, we call it as clay soil. Okay, so we call it as clay soil. Now, these clays are actually, how do I say? These clays actually have to be defined with the help of some more parameters. Okay, those parameters we will see here in the topic consistency of clays. Now, now, what is consistency? What do you mean by consistency? Consistency is nothing but the degree of firmness. Okay, degree is how soft or how hard the soil. So clay, you all know. What is clay? You all know. Yeah, clay. What to some? If you whenever I tell clay to you, something comes to your mind, right? So this is clay, clay thing, clay material, right? Okay, so that clay, the firmness of the clay, whether it is hard, very hard, or very soft, that is the consistency of the clay. Now into demarcate, okay, to demarcate this consistency, okay, in order to demarcate this consistency, uh, we have this uh, limits known as Atterberg limits. Atterberg limits are very important properties only particularly for clays. This actually demarcate the boundary. Okay, demarcate or they actually give the it actually gives the boundary. Okay, which defines the degree of firmness or the consistency of the clay. Okay, okay. So now if you mix a fine grained soil, okay, fine grained soil, remember whenever I say fine grained means most of the portion of the soil particles is lesser than 75 microns, right? That's why it is called a fine grained soil. So now, if for a fine grained soil, you keep on mixing water in it, what will happen? It will just keep on flowing as a liquid, right? The soil will actually lose all its strength and it will be just very liquidy, fluidy, liquidy, right? The soil will be like that. So that limit above which the soil turns into a liquid is nothing but the liquid limit. Above the liquid limit, if the water content is high, nothing but that is the liquid state. Okay, the soil will turn into a liquid state. So here you can see one plot is given volume versus water content. Okay, so this is the Atterberg limit. Now, if you say reduce the water content a little bit, then we enter the plastic state. Plastic state is where the potters actually use to make the pottery or something. Give certain shapes, certain idols are made, certain whatever, and showpieces you can make with soil. But that the potters actually work in this plastic range. Okay, so so keep on so this region is where the soil is actually plastic is actually defined by the plasticity limit. So between the plastic limit, so this plastic limit is WP, and between the liquid limit, the soil is actually plasticky, that is moldable, right? Then again, if you keep on reducing the water level, you will reach a semi-solid state. Then further, if you reduce the water level, okay, there will come a stage which is known where the soil will become totally solid. Okay, so here it comes the shrinkage limit. The shrinkage limit after the shrinkage, so you can see that as you are reducing the water content, the volume is also reducing. That as you are reducing the water content, the volume is also reducing. But after you reach the shrinkage limit, even if you reduce the water content, the volume is constant. Okay, the volume is constant. Okay. Now, this shrinkage limit is the point till which the soil is 100% saturated, fully saturated. You can recall solids, water, air. Till shrinkage limit, this total portion is occupied by water. Okay, this total portion is occupied by water. Now from here, if you keep on reducing the water content farther below, what will happen? The soil will keep on drying out. So here it is completely dry state. Okay, so this total volume doesn't change, right, from here. So that's why shrinkage limit is the point up to the point till which the soil is completely saturated. Below the shrinkage limit, the soil is no more fully saturated, and at 0 water content, obviously it's completely dry. Okay, so liquid limit, plastic limit, and shrinkage limit. These are the main three limits. Above liquid limit, if you pour water, soil will turn into liquid. Above plastic limit, between liquid limit, it will be plasticky, moldable. Between shrinkage limit and plastic limit, the soil is a semi-solid, and below the shrinkage limit, it will be solid soil. All right. Now, how to determine liquid limit and plastic limit? So, what we do in order to determine the liquid limit, plastic limit, we use the Casagrande. So, you use this liquid limit apparatus. Okay. So, this is the liquid limit apparatus which you see here. Okay. The photo of which you can see here. So, it is a cup. It is a base below. What we do, we pour, we take some soil grains, okay, passing through 425 microns. Okay, soil passing through 425 microns, we take, we pour some water, some amount of water, we make a paste, and then we apply it on the, we evenly spread it on the this cup. Okay, we evenly spread it on the cup. Okay, evenly spread it on the cup. After we spread it on the cup, what we do, we, there is a handle at the side. Okay, at the side here, or here, one side there is a handle. So when we turn that handle, what happens? This cup actually, say this is the base. This cup, it hits like keep tuck tuck tuck. It will keep on hitting the base. Okay, like this we need to give 25 number of blows. And before playing the blows, one thing which before doing this, the main thing what we need to do is that you need to make a groove. Like this, you need to cut a groove into the soil. How to cut that groove? There are two tools to cut. One is a Casa Grande apparatus and other is a ASTM tool. One tool is shaped somewhat like this, and one tool is actually like something like this. You can see it in the internet, the images or in your lab. So one is the Casa Grande tool and another is the ASTM tool. So for completely clays, we use generally the Casa Grande tool, and for silty soil, we use this ASTM tool. So what happens? We cut a groove in the cup. After cutting the groove, actually we start giving the blows. Okay, we start giving the blows. So how many blows are we going to give? We keep on giving the blows till the time 13 mm for Kasaganda apparatus, 13 mm distance. Okay, 13 mm distance between these grooves is actually between the space is actually taken again by the, so you cut a groove like this, and this is the soil, this is was the soil, so you make a groove in between, so this soil is like this right now. Now keep on giving blows to the cupboard, the soil will come, start coming close, it will come, start coming close. Now till the time 13 mm distance has actually been covered like this, close like this, 13 mm, this is 13 mm approximately. We need to note down the blows. So you add some water. So you make the paste. You had made the paste by pouring some amount of water. Then you keep on giving blows. So what will happen? Say first you had given very less water, so it took high number of blows. Say 35 number of blows it took for 10% water. Then we increase the water 20%. Then it took say 27 blows. Then say you increase to 25%, it took 25 blows. Then you increase the water to 30%, it took more 20 15 blows. Like this you need to do. After doing that, what we need to do is that we need to plot a graph between the number of blows and the water content. Okay, number of blows and the water content. So this is actually in log scale. Okay, in log scale, this is plotted, and you will get a graph something like this. Now corresponding to 25 number of blows, whatever. So we have various points like this. We got various points. Whatever number of water content you get, that is nothing but the liquid. Okay, this is the liquid. And for plastic limit, what you need to do? Uh, uh, you need to take the soil in the hand and then keep on like making a roll like this. So the moment at which a 3 mm diameter string, okay, string of soil just begins to crumble, that point is the plastic limit. So to get that, what you do? Say we're rolling at 3 mm, it becomes to crumble. That means you have reached the plastic limit. Then we take that soil, you put in the oven, and then you get the water. Okay. Next, we have the plasticity index. So what is the plasticity index? Plasticity index is nothing but IP is nothing but the liquid limit minus the plastic limit. High plasticity index means highly plastic. Okay, low plasticity index means non-plastic. Okay, then we have relative density. Relative density or D% is nothing but E max minus E natural by E max minus 200%. That means Emax is nothing but this is actually relative density is really valid for coarse soil. Okay, so relative density gives a degree of denseness of that coarse grained soil. Okay, so Emax means the loosest state in which that soil can exist. That word ratio is nothing but the Emax. E natural means the place where you are measuring the relative density, there the in situ word ratio, that is the natural, and E mean is nothing but the densest state, the densest state of that soil. What is the word ratio that is possible? Is nothing but the relative density. This will give you that relative this relation. This is generally valid only for cohesionless soil, that is the coarse grained soil, not fine grained soil, coarse grained soil. Okay. So that was all. So let us start solving the problems as slowly. Yep, this first week is actually nothing very easy, just basic stuff. Just start solving the problems. Okay. Just a second. Okay. Yeah. Okay. So the first question: a soil sampler of a soil sampler of 1000 cc is used to collect soil samples. It was found that the sampler contains 2 kg soil with dry unit weight of 1800 kg per meter cube. If 400 gram is mixed to the soil, then what will be the water content of the sample? We need to find out. Okay. So first, what we will do, we will find out the initial water content, and then okay, we'll see. Okay, initial water content, then we can find the later water. Well, let us see how to do that. Let's see, step by step, we'll go slowly. So we have a soil, right? We will have a soil where volume is 1000 cc total volume sampler. Okay. So in that sample, we have total 2 kg soil, and the dry unit weight is 1800, or dry density is 1800 kg per meter cube. Okay, this is the dry density. So if this is the dry density, so what is dry density? Weight of soil solids by total volume. Now from here, what we can do, we can get the weight of soil solids 1800 into 1000 cc, right? 1000 cc is how much meter cube? 10 to the power minus 6. So it is nothing but 1.8 kg. So here in this 2 kg soil, initially 1.8 is weight of solids. If 1.8 is weight of solids, let's try it properly. If 1.8 is weight of solids, then 0.2 is what? Weight of water. So weight of water is nothing but 0.2 kg. Done. Now we have to find out if 400 gram of water is mixed to this sample. Now the new weight of water will be what? 0.2 plus 0.4, 0.6 kg. Because 400 gram we are adding. What will be the water content? So what is water for relation? Weight of water by weight of solid into 100%. So what is weight of water? 0.6. Weight of solid 1.8 into 100%. How much? 33.33%. Okay, 33.33%. Right? Understood? How we did this very simple problem. Straightforward. Let us go to the next problem. This is also very simple, similar to the previous one. An oven dry soil has a specific gravity 1.5 gram per cc, with the bulk density of the soil in its natural state 2 gram per cc. And what is the water content of the soil in its natural state? An oven dried soil has a specific gravity of 1.5 gram per cc. Oven dried soil. Okay, it is the dry. This is the dry unit, nothing but the dry density. If the bulk density of the soil in its natural state is 2 gram per cc, and what is the water content in the natural state? Now, say the total volume is 1 cc. In 1 cc, 1.5 gram is actually occupied by uh, what? Is occupied by soil solids. Okay. Right. Now, in bulk density of soil in natural state is 2 gram per cc. Okay, in its natural state, 2 gram per cc means what? In this 2 gram per cc, as we all know, 1.5 gram is obviously the soil solids. So in this 2 gram, 1.5 gram is soil. So rest 0.5 is what? Water, isn't it? So what will the water content? 0.5 by 1.5 into 100%. Nothing but 33.33%. So easy, extremely easy. Don't have to use anything, any formula or anything, just basic concept you're using. Then one more way you can do. What we can do is that there is one relation. Okay. There is one relation that dry density is total density or bulk density 1 plus water content. So what is the dry density? 1.5. What is the total density? 2. 1 plus water. From here, water content starting but 2 by 1.5 minus 1. 2 by 1.5 minus 1. Sorry, 1 by 3. 33.33%. So we can do this way. Using relation also you can just or by basic concept you can do this. Okay, so very simple. So first, how did I solve it? It is given overnight soil is a specific gravity 1.5 gram per cc. Okay, so in 1 cc volume 1.5 gram soil solids are there. Right. Now second part, if you come, the bulk density of the soil is natural state is 2 gram per cc. So obviously in this, if the bulk density 2 gram, in this 2 gram 1.5 is contributed by the soil solids. And if 1.5 is contributed by the soil solids, the rest 0.5 is going to be contributed by the water. So obviously 0.5 is the weight of the water. So done. 0.5 by 0.5 into percent. Simple. Right? Okay. Let us see the next problem. Consider the phase diagram shown in figure and determine the water content, void ratio. Okay. Water content, void ratio, saturated unit rate. Okay, given the specific gravity of soil solids is 2.6. Right. Here are the phase diagram shown. Phase diagram is given. So in the phase diagram, if we see the weight of soil solids is given, the weight of water is given. What we need to do? We need to determine the water content, the void ratio, and all other stuff. So let us do. G is given. G is given as 2.6 or 1. Now what is water content? Weight of water by weight of solids. So what is weight of water? 20, 100. Get percent. Easy, very easy. Next we have void ratio. What is void ratio? Volume of voids by total volume. Right. So this is the basic definition. Or we have a relation S equal to WG. From here you can get it. E is nothing but W into G by S. So what is the S? So here if you see the phase diagram, okay, remember this relation. Okay, so if you see the phase diagram, you can see that there are no voids. All the voids are occupied by water. That means saturation is 1. So S is 1. So S equal to WG 0.20 into G 2.6 is nothing but 0.5. Very simple. Then comes the porosity. So there is a relation between porosity and their word ratio. Remember this relation. So you can just put the value. Okay. Last. Okay. This much only I think. And saturated. Sorry. We need to find out saturated. So there is a relation for bulk. So bulk density is given by G plus AC by 1 plus C comma W. Okay. Now for fully saturated, S is equal to 1. So gamma sat, you just put S equal to 1 here. G plus E by 1 plus C gamma. What is G? 2.6 plus E you found out 1 plus 0.52 into 1. So whatever it comes, come. Okay, let me do it then. 0.6 plus 0.52 by 1.552 20.14. Okay, very easy and simple. Okay, next problem. Soil, let me just have some water. Just give me a second. Huh? Uh, so meanwhile, just read this question once. Just go through this question once. See if you can visualize this problem. I will just get back to it in a minute. Okay. Okay. So a soil sample A, right? A soil sample A and B have void ratio of 0.5 and 7 respectively. All right. So there are two soil samples, A and B. A has a void ratio of 0.5 and B has a void ratio of 0.7. Okay. If 1.5 meter cube of soil sample A and 1.7 meter cube of soil sample B are mixed to form sample C, having a volume of 3.2 meter cube, what is the porosity? Sorry, what is the porosity of the sample C? Okay, the porosity of sample C. So soil sample A and B, the void ratios are given, and 1.5 meter of soil sample A and 1.7 meter cube of soil sample B are actually mixed to form a sample C. And the total, obviously, the volumes are going to get combined. So 3.2 meter cube of, for example, C. So we need to find the porosity of sample C. Okay. Okay. So how do we proceed? How do we proceed? So what is the, after mixing, what is the thing that we have to equate? That is the question. Okay. What is the thing that we have to equate? That is the question. So first, let us just write, okay, whatever we know. For A, this for A, void ratio is 0.5. Volume is, total volume is V A. Here A doesn't means air. A means total volume of total volume of A. Okay. Is 1.5 meter cube. For B, for C, EC, void ratio we don't know. And VC we know. Now, now, say for 1. So this is the volume of solids of 1, and this is the volume of voids of A. This is the total volume, right? So what is the void ratio? Void ratio definition, volume of voids by total volume. So volume of E into V. So V, so this V is nothing but E into V. I'm writing A here because it's for A plus Vs A, right? E into V A plus Vs A, isn't it? Let me write for clarity. Okay. Okay. Right. Is total volume is volume of voids of A and volume of solids of A. Volume of voids of A I can write E into A A. Isn't it? What I am making some mistake. Huh? Okay. Yeah. Yeah, I was making some mistake, right? Isn't it? I was making some mistake while writing this. What was the mistake? What is A? See, the mistake is volume of, what is the definition of void ratio? Just erase it. It should be volume of voids by volume of solids of A, right? This is the definition. It's this. So volume, total volume of A is nothing but EVSA plus VSA. So VSA, if I common 1 plus EA, right? right? So from here, I can write V volume of solids of A is nothing but volume of A by 1 plus A. So volume of solids of A I can calculate. So what will be that? 0.5. Okay, right. This will be nothing but 1 meter cube. Similarly, PSB VB by 1 plus EB. Same again 1 meter cube. Therefore, when you are mixing A and B, the volume of solids are going to be constant. So when you are mixing, what is the volume? What in mixing and making a sample C? What will be the volume of solids of C? Therefore, volume of solids of C is nothing but 1 plus 1 equal to 2 meter cube. Right? This plus this 2 meter cube. Okay. So this is the volume of solids. Now, if I get the volume of solids, okay, if I can get this volume of solids of C, I can get the volume of voids of C. Volume of voids of C what? Volume of C minus volume of solids of C. Volume of C is 3.2 minus 2. So 1.2. Done. So now finally I can get the porosity. N of C is nothing but volume of voids of C by volume of C. 1.2 by 3.2 and 375. Done. Quite simple, right? So the volume of solids are going to be constant, right? So volume of solids of A I found out, volume of solids of B I found out. So if I'm mixing both of them, the sample I'm getting, that sample is going to have volume of solids of A plus B, right? 1 plus 1, 2. Now what is the total volume of the sample C? It is 3.2, 3.2 meter cube. Out of 3.2 meter cube, 2 meter cube is occupied by the volume of solids. So if 2 meter cube is occupied by the volume of solids, so 3.2 minus 2, 1.2 meter cube is occupied by the volume of voids. If I know the volume of voids, now we can determine the porosity. Right? That's all. Simple. Okay. The next problem, a sampler with a volume of 60 cc is filled with saturated soil sample. A specific gravity of soil solids is 2.65. When the oven dry soil is poured into a graduated cylinder filled with water, it displaces 40 cc of water. What is the natural moisture content and the dry unit weight of soil? A sampler with a volume of 60 cc is filled with the saturated soil sample. Okay, with 60 cc is filled with saturated soil sample. The specific gravity of soil solids is 2.65, and specific gravity is 2.65. When oven dry soil is poured into a graduated, okay. So when an oven dry soil, see, totals from this line, when the oven dried soil is poured into a graduated cylinder filled with water, it displaces 40 cc of water. This means what? This means the volume of this solids. The volume of soil solids is 40 cc. Right? When a dry soil is poured into a cylinder, it displaces 40 cc. Right? It displaces 40 cc. That means what? That means that the volume of the soil solids is nothing but 40 cc. So on this line, we can write volume of soil solids is 40 centimeter cube. Right? Now, what is the total volume? Sampler volume. Sampler volume is 60 cm. Now, in 60 cm cube, 40 cm cube is going to be occupied obviously by the soil solids only. So, what is the volume of voids? Sorry, right? Right now, can we find out the void ratio from here? Volume of voids by volume of solids. Done. Done. Now, this sampler 60 cc whatever we are solving, for which we need to find the natural moisture content and the dry nitrate, that is a saturated soil sample. It's given here saturated. So S is equal to 1 we know, E is 0.5 we know, right? We know this. So water content we can find out. SC is equal to WG. G is given 2.65. So W is 1 into 0.5 by 2.65. This is going to come out as 18.86%. So this is nothing but the natural moisture content. Okay, 18.86. Next, you need to find out the dry unit weight. So what is the dry unit weight? Dry unit weight is nothing but weight of soil solids by total volume, right? But what we can do, we can use the relation that we just discussed two problems back. So what is that? What was the relation? Gamma bulk is G plus for saturated. This is the relation. So if I put 2.65 plus 0.5 by 1 plus 0.5, so I can get 10 from here 2.1 gram per cc. Right, this is the bulk density. Now if I want to find a dry density is nothing but, remember these relations, okay? Bulk density, so 2.1 plus 0.1886. So this is going to come out as, understood? So first, from this line, whenever that sample is poured into regenerated cylinder with filled with water, is filled with 40 cc of water. From there, we have to track. You have to crack that the volume of soil solids is 40 cc obviously. Now we know the total volume, we know the volume of soil solids, you can get the volume of voids. Now if you know the volume of voids, you can get the void ratio. Now if you know the void ratio, you know the saturation is 100%, we can find, we know the G, we can find out the natural moisture content or the water content. After you know the water content, what you can do? You can find out the total unit weight, bulk unit weight, the bulk unit weight, yeah, the bulk unit weight, and from the bulk unit weight, you can find out the dry unit weight. Okay, so this is how you need to solve it. Unit weight, if we call this unit weight, it's actually wrong. It's density, bulk density, because the unit you have to see gram per cc, weight, mass per volume. If it would have been kilonewton per meter cube like that, you would have called it, you would have used gamma and you would have called it unit weight. But now we are calling it at, it would be better if you call it as density, dry density, uh, dry, this one. Bulk density, if we call it, it will be appropriate, more appropriate. Okay, more appropriate. Okay, so let us solve the next problem. Compacted cylinder specimen of 50 dia and 100 long is to be prepared from dry soil. If the specimen is required to have a water content of 15% and the percent of air void is 20%, calculate the weight of the soil and the water required preparation of the soil specific degrees to 0.69. Okay, let us see. Okay, so a compacted cylinder. So specific the dimension of a cylinder are given. Okay, so what will be the volume of soil sample? The volume of soil sample is going to be nothing but the volume of cylinder. We do if you put all this pi by 4 d in place of d, if you put 50 and the h if you put 100 we'll get centimeter cube. Right now, what is water content? Water content is weight of water by weight of solids. Weight of water, how we can write? We can write volume of water into unit weight of water, and weight of solids also we can write volume of solids into yeah, S will be more appropriate, I guess. Density. So now from here we can write volume of water by volume of solids into G. This we can write because this is nothing but G. Nothing but G. Now, the cement is required to be water content of 15%. Okay, so 0.15 let us put. G from here, if we want to write VW, we can write as uh, so okay, we get this relation. Right, we got this relation. Now, what we can do, we know, okay, this is what? Percentage air voids is 20%. It's given. One more given quantity. So first we use two given quantities are given. So two equations we can get. So one given quantity is water content. From there we got one equation. The second, so one relation. Then second given quantity is the percentage air voids. From there we can get one more relation. Right? So this is nothing but 0.2. It's given. So we can have volume of air is nothing but 0.2 total. Right? Now what is the total volume? Volume. This plus volume of water plus volume of air, volume of soil solids plus volume of water plus volume of air. Right? From here, volume of soil solids. So this relation we can use now. VW equal to 0.4 Vs. VA 0.2 V. So now if you do, you will get one relation 0.8 0.8 0. Sorry 1.4, right? Vs. You got this, then Vs is nothing but 0.8 V by 1.4. So 0.8 into total volume, 196.35. Put 196.35 by cube, right? Therefore, what is weight of water? What is weight of water? Uh, Sorry, weight of solid, not weight of water. What am I saying? Weight of solids. Weight of solids is what? Volume of solids into unit weight of solids, right? So this into gamma W, if I do, this will give me the unit weight of solids into the volume of solids, right? So what is G? Put this I put 1 gram per cc and Vs is get 301.829. Okay, this is the weight of solid. The weight of water, if I want to find out, nothing but 0.15 into WS, because 0.15 is the water content. Okay, so like this you need to find out. Finally, the weight of required, what weight of water required is this much. So we use the given two quantities, percentage air volume and water content, to put in the relation. And from using that relation, what we did, that relation, and using the known quantities, we just determine the volume of soil solids. Now, volume of soil solids, if we know, we can get the weight of soil solids. The weight of soil solids, if we know, we can get the weight of water from the using the water content. Okay. Okay, next is the borrow pit problem. An embankment is to be constructed. The soil is to be compacted at a maximum dry density of 18 kilonewton per meter cube at an optimum moisture content of 15%. That is at 15% moisture content, we need to compact it. The in situ bulk density and water content, the borrow pit are 17 kilonewton per meter cube and 8% respectively. How much excavation should be carried in borrow cube for each meter cube? Okay, so there is a borrow pit. Borrow pit means there is some place from where you have to excavate the soil and carry to some other place and build an embankment. From one place you need to carry the soil to build an embankment at the other place. Right? Now the properties of the borrow pit are given and the required properties of the embankment are given. So the embankment should have an 15% OMC, 15% water content at and have a dry density of 18. And initially at the borrow pit from where you are taking the soil, there the bulk density is 17 kilonewton per meter cube and the water content is 8%. So how much excavation or how much volume should you excavate in order to make 1 meter cube of embankment? That you need to find out. Okay, so you need to construct 1 meter cube of embankment at 18 kilonewton per meter cube density at an OMC of 15%. How much excavation do you have to do at that place from where you are carrying the soil? This is the problem. Interesting problem, right? So first, let us write everything whatever is given. Okay. So borrow pit, let us call it 1. So borrow pit density is 17 kilonewton per meter cube. Water content is 0.08%. G is 2.7. Embankment, let us call it 2. Right? Right? So what we can do for this, we can find out the dry density of 2, required dry density. We can find out how to find a dry density. How to find out sorry, the dry density is given. How to find the bulk density? The bulk density is nothing but what? Dry density is nothing but bulk density 1 plus water content. So from here, this bulk density of 2, that is at the embankment, we can find out whatever we need to maintain. 1 plus 0.15 into 18. Okay, this is the dry density. Dry density. Okay. So the bulk density at 2 is 20.7 kilonewton per meter cube. Now, what we have to do is first we need to find out the void ratio at the this border pit. Okay, so how do we do that? You know this G plus SE is equal to 0. So this relation, if I put C1 into gamma W. So what is bulk density at the borrow pit? Bulk density borrow pit 17. 2.7 is given. Water content is also given 0.8%, 0.08. 10. Let us take it as 10. 9.81. So just we are taking 10. Okay, 10 say. 10 say it is 10. So from here E1 I will get as 0.7153. Okay, this is the E1. Void ratio at. Now again gamma 2. From here, if I put all the data, gamma 2 I have found out 20.7. This is what 20.7. So if I put this, if I put 15, 0.15, everything if I put, E2 will be coming out as 0.5. So I need to reduce the void ratio, right? So initially at the bottom pit, the void ratio is 0.7, but I have to reduce it to 0.5 and I put it in the to construct the amendment. Now, the soil solids that you are going to carry from here to here, because that is the same soil you're carrying, right? So soil solids are going to remain the same, right? The amount of whatever volume you are excavating, that volume you are going to put in there. So there the soil solids are it's going to be the constant, right? So whatever soil you are taking, whatever soil, so there the soil will have some water, some air, right? But the soil solid amount of soil solids, so the volume of soil solids are going to be constant here also, right? The soil solids are going to occupy the same volume, isn't it? They're going to occupy the same volume. So what I can do is that I can write like this from here. Right? So if I put all the data, what is V2? V2 is for every 1 meter cube. Every 1 meter cube, right? So 1 plus 0. So V1 will come out as 1.143 meter cube. So for constructing 1 meter cube of the embankment, I have to excavate 1.143 meter cube of the soil at the pit. So 1.143 meter cube soil will be accommodated to construct 1 meter cube of embankment. So obviously you can the volume will be reducing, right? So word issue is reducing, density is going to increase. That's how we are going to maintain the density, maintain the word ratio. Okay, I hope you get this volume. Okay, just revise it once, everything will be crystal clear to you. Okay, the next is very simple. Relative density test was conducted on a sandy soil. The following test results were obtained. Emax is given, Emin is given, ID is given. The calculate dry density of the soil. Okay, let's divide to. Let us just do step by step. So ID is what? Emax minus E natural by Emax minus E. Right, so 45% is 0.45. Emax is 0.95 minus E by 0.95 minus 0.4. So what is the void ratio? Void ratio will be this much. Okay. Calculate. Okay. Now calculate the dry density of the soil. Dry density of the soil is nothing but G gamma W by 1 plus E. Remember these relations. G is 2.7 into gamma W is gamma WC for density, right? So let us calculate it gram per cc. So 1, you put 1, 7, it will be 1.588 gram per cc. This is the dry density of the soil. If a 5 meter thickness of the stratum is densified to 70%. So initially densification was 45%. Now we are more densifying it to 70%. Okay, now if you densify it to 70%, so what will be the void ratio? Same, find it out. The new void ratio is going to be 0.565. Right, 565. Right. Now consider, say you are asked if a 5 meter thickness of the stratum is densified, how much will the stratum reduce in thickness? Okay. So initially say that stratum was 5 meter thick. Okay, this is 5 meter. And consider that other all dimensions are 1 meter, 1 meter. Okay. The total volume, what is the volume? Total volume is going to be 5 into 1 into 1 is 5 meter cube. Right. Now, what is E? E is volume of voids by volume of solids. So V1 minus Vs by V is 1. Vs. So E I know 0.70. V1 I know it's 5. So from this relation I can get Vs is equal to 2.94 meter cube. Now E2. Again volume of voids by volume of solids. Yeah, volume of voids is V2 minus Vs by Vs. So volume of solids are going to be constant. So E2 is nothing but 0.565. Right. So V2 total volume minus Vs 2.94 by 2.94. We do, we will get V2s 4.601 meter cube. So this much volume is initially, if it is a 5 meter cube, after densification, the volume has reduced to 4.601 meter cube. So there's so we can say that the height change is nothing but 5 minus 4.601, approximately 0.4 meters. Okay, okay, approximately you can say that. I hope this was clear, right? So what we did first, we found out both the void ratios. Both the void ratios, then we know the initial volume 5 meter cube was the initial volume, say 5 meter height, one say cube say, sorry, parallelepiped say 5 meter cube. From there we determine the volume of solids. The volume of solids are going to be constant always. Whether we compact it later, so volume of solids are going to be densify it. The volume of solids are going to be always constant. So using that volume of solids that we found out and the new void ratio, we got the new total volume. Total volume. From total volume, we could get the height change. Okay. So find the liquid limit from the data of the liquid limit using the second table. So this is there is a number of, as I said, number of flows are given and the water content is given. You need to plot this in log scale. You will get a graph like this and corresponding to 25 number of flows. Whatever value comes, that is your liquid limit. So I have done this in Excel, so you can see number of blows are plotted against the water content in a semi-log graph. So just we will draw a approximate graph graph like this, and from here, here if I calculate like this, so we will get something approximately close to say 70% something. Will get like this. Okay, this really is nothing but a liquid limit. Approximately 70%. Okay, and this graph is actually known as the flow line. Okay, this is nothing but the flow line. And the slope is actually known as flow index. This is known as flow line, and the slope is known as flow index. Okay. Next, overnight sample of 200 cc weighs 360 gram. If the specific gravity is 2.7, determine the void ratio and seepage limit. Okay, so the oven dried sample volume. So volume of dried sample it's given. So yeah, so volume of dried sample is 200 cc. Weight of solids I can write from here is 360. Specific gravity is 2.7. I need to determine void ratio and shrinkage limit. So I will just do it for you. Dry unit weight 360 by 200 per cc. Gamma dry is G gamma W by 1 plus C. So 1.8 is equal to 2.7 into 1 by 1 plus E. From here you can get E as 0.5. Just use the relations and find everything. It's very simple. Okay, now the main things come. See, initially it is very easy to determine. Okay? E is very easy to determine. So volume you have, total volume you have, uh, weight of soil solids you have. You can find out a dry density. From dry density, you can find out the void ratio using this relation. Okay, you can get the void ratio from here. Now, for shrinkage limit, if you remember, what is shrinkage limit? This is the shrinkage limit. Okay, so the volume here when the soil is completely dry, that is zero, and the volume at shrinkage limit is absolutely same. So what is the volume? Right, it's absolutely same. So now at shrinkage limit, what the soil is perfectly saturated. Remember, I told you, soil is completely saturated only up to this level. If you go keep on reducing beyond that, the water content, the soil won't be saturated anymore. Okay, the soil is completely saturated. Now, if we use the relation from here, we can get the water content 1 into 0.5 by 2.7. Okay, this water content you can get. So this is the actually the water content that shrinkage limit that is the shrinkage limit. Okay, so therefore shrinkage limit is okay. So the void ratio here 0.5. The volume is remaining same. So volume of voids by volume of sorry, the volume of voids is always the same, right? So this volume of voids, whatever it's there, whatever it is here also, the volume of void is that only 0.5 here, also there also at shrinkage limit also at 0.5, isn't it? So that's how we find it out. Now the last problem. Okay, for today, this will be the last problem. The mass specific gravity of fully saturated specimen of clay having a water content of 40%. This is 1.88. On oven drying, the mass specific gravity drops to 1.74. Calculate the specific gravity of and its shrinkage limit. Okay, so mass specific gravity is nothing but right. So now for saturated sample, total is nothing but the saturated unit weight. Right. So what is the saturated unit weight? This much. Now GM. Now if you do GM is nothing but G plus E by 1 plus E gamma W by gamma W. So gamma W cancel. Right. So the mass specific gravity is what given 1.88. G plus E by E. This is one relation. Okay. This G is gravity of soil solids. Okay. This is the specific gravity of soil solids. Right. Mass specific gravity is different. This is the mass specific gravity. Now this relation we got. Now one more relation we can get SE is WG. So at saturation S equal to 1 and what is the water content? Fully saturated water content 40%. So 1 into E is equal to 0.4 into G. So E is equal to 0.4 G. One more relation you got. So if we put this here, if we put this here in place of E, you can get the G mass, the specific gravity as 2.9. Okay. Okay. Now the question is, second part is now when drying, the mass specific gravity drops to 1.74. That means the new mass specific gravity is 1.74. This is nothing but again gamma. See, same relation gamma T by gamma W. Now what? Now on oven drying, right? So oven drying T will be dry. So this is the relation. So gamma D by gamma W is nothing but 1.74. Okay. Now this is one important relation that you can remember, and a shrinkage limit by 100. Okay. So here you can 4 minus 100. Now if you solve this, you can get the shrinkage limit as 0%. Okay. Okay. So that was all for today. Sorry. Yeah. So that was all for today. With this, we will end today's session. And I hope that this was helpful for you. And if there is any doubt, please feel free to contact me anytime. Okay. So thank you. So see you in the next class. Thank you.